Apparently, I've been introduced. I know absolutely no Russian. I'm sorry. Thank you for that presumably warm introduction. I don't know if it was or not, but I think it probably must have been. So, I'm Michael Bolton. No, I'm not the singer. No, I'm not the guy in Office Space. No, I'm not the clown who just got put into a position of authority in the United States. I hope we see the end of him soon. All right. I'm going to talk today about the logic of verification. And I want to make this really clear from the beginning that verification is not a bad thing. Verification is not a bad thing, but I think there's a common problem in our business that we don't think very deeply about things. And there's a few of us who like to do that. And so I'm going to invite you to come with me as we investigate this idea of verification, which is, according to some people, at the center of testing. We have a product. And we're not sure about the quality of a product. That's the case. That's why we test. Let's call that product P. Easy way to refer to it. Now, one way to evaluate some things about P is to put it inside another system. And so we'll call that system C for checks. I know that looks like S to you, but it looks like C to me. We design C to provide P with input, and then to run it, to operate it. And C then observes P, and it collects output from it, and then it compares that output to a specified result. And then C provides a report on the outcome of the comparison. Now, after this process, you might think this way about what's going on. If C reports no problems, then we have verified that P is a good product. And if C does report problems, then we have verified that P is a bad product. But what's really happening? Let's go deep. Let's go deep into the idea of verification and see what we can find. So let's go to the dictionary first of all. To verify in the dictionary means to ascertain or confirm or to check or to test the truth or accuracy of something, to assert or prove something to be true, to testify to the truth of something, to support a statement or a law, a hypothesis or a theory. And then this weird one, which is to check items of data input for accuracy, for example, by having the same data keyed twice by two separate operators and then checked by a computer for discrepancies. That's oddly specific. Were they wearing any particular color lab coat when they did this? In the rapid software testing namespace, we say that verification is the sort of universal definition of verification, the idea, the process of establishing the truth of a proposition or a statement. And it's not particularly specific to software. In regulated software, verification is the process of comparing a product to its specification. That's distinct from validation, which people also talk about in the same breath, which is the process of trying to figure out how well it will fit or fulfill its ultimate purpose. So, let's go deeper still. Something exists. Some of what exists can be known. Some of that can be described in words. And some of those words can be used or expressed as propositions which are either true or false. So, once again, verification is a process of establishing whether something is true or false. It's not a feeling. Verification is a form of reasoning through logic within a logical system. So, for instance, x plus y equals 2. That has a truth value, and it can be verified as true or false if you know what x is, and you know what y is, and if they're numbers, and if the conventions of arithmetic apply. Okay? X plus y equals 2 may have a truth value that's unverifiable if the conventions of arithmetic apply and x and y are numbers, but the value of x and y are unknown. In other words, there's an infinite number of possible cases, possible values that x and y can hold, and if we don't know what those are, the proposition x plus y equals 2 does not have a verifiable truth value. X plus yin-yang equals 2 does not have a verifiable truth value if the conventions of mathematics apply, because yin-yang doesn't have a mathematical value. We chose the symbol yin-yang because it looks nice, and it starts with y, but it doesn't stand for anything in particular. What's that? We just declared that it doesn't. That's the premise that we're working from there. It could, absolutely. If we knew that it stood for something, x plus yin-yang would have a truth value. So, by the way, you're welcome to ask questions. If I can hear you, you might have to shout loud because the room is designed for sound to go that way instead of this way. So, in a system that has lots of state spaces associated with it, we may be able to show that x plus y equals 2 many times, 10 times in a row, yet it might be false the next time we try, the next time we look. So if we find that it's true even once, we can verify that it can be true. But unless you're checking every possible state of the system, including states that you don't know are possible, you can't verify that x plus y will be true. X plus y equals 2 will be true. So propositions without a truth value can't be verified. There's a famous example in linguistics, a sentence that comes from Noam Chomsky: colorless green ideas sleep furiously. Well, that doesn't have a truth value. Ideas don't have a color. They're not green. And if they're green, they're not colorless. And so far as we know, ideas don't sleep. And if they slept, they probably wouldn't sleep furiously. There's no truth value associated with this. Although it's syntactically correct, the semantics are all messed up. Another problem with verification is that statements about the future can't be true, can't be verified, until we reach the future. So we can say that there are no bugs in the product that we're aware of so far. Our checks will find all the bugs in the product. Well, that's not a verifiable thing. We hope it's true. Customers will be satisfied with this product. That's not verifiable either. We believe it will be true based on testing, but we can't verify that unless we have a time machine. We could verify a statement about the future if we had a time machine and we went to a set point in the future, and then we asked all the customers, were you satisfied with the product? Are you satisfied now? And they would say yes, and then we come back and we can say, yep, they were satisfied, or they will be satisfied. Except, even then, they'll only be satisfied up to the point that we arrived at and that we asked them about. All right, how does this relate to software testing? Let's bring it in. The product is currently not in a crash state. That is a verifiable statement. We can know that here and now, but the fact that it's true doesn't tell us anything about what the product will be doing 5 minutes from now. Maybe it will crash if I press the wrong key. Maybe it will crash based on an interrupt coming in from outside. Maybe it will crash based on some computation that is happening in the background that we don't know about and that we can't see. So, what we care about is that the product shall not crash, but that can't be verified empirically. Another example. I am able to read all the buttons on this screen. That we can verify. We can know that here and now. We can even have somebody else do it, and they can say that, yep, they can read all the buttons on this screen, but that doesn't mean that it's going to be true for all of the buttons at all times, running on all browsers, in every possible state of the product, for every kind of person, under all lighting conditions, including people who are colorblind. What we care about is that the product shall be reasonably easy to use, but that can't be verified empirically either. It can be tested, but it can't be verified. I recognize the sign-up screen, and I don't see any problems. That's knowable here and now. But it's not knowable for every situation what screen should be displayed, that it's compatible with all the browsers, that all the links and JavaScript and everything works properly. What we care about is the correct sign-up screen shall be displayed. That's not available for verification. It can't be verified empirically. So verification isn't exactly testing. It might inform testing, but it's not testing. To say the product is very good means something like, this product is very yin-yang, based on what we know about the variables and their states, and plus all of our assumptions about those unknown variables and those unknown states, unverifiable, but we can test it. We can test the theory that the product is very good. The thing is that testing is way more than verification. I got a couple of little examples here. Several years ago, I was working at a bank in Canada, and the assignment that was given to me was to test foreign exchange. So some of you will be working in a domain where that's familiar. And there were 5 or 6 other testers working alongside me, and they were working through a big set of binders, a big set of books that had pages that they would flip through, and there were scripts on each page which said, perform this action, and then perform this action, and then perform this action, and then verify that you get the correct result. It was the most boring kind of work I could have imagined. And what was more was they weren't really finding very many problems in the product, except for one thing. These scripts had been written about a year earlier, and they referred to an older version of the product. And sometimes the text on one side of the page disagreed with the image, the screen capture, the screenshot on the other side of the page, and so they would report problems like that, but they didn't investigate the product very much. They followed a procedure as though they were interesting-looking machines. And they didn't find very many bugs. On the other hand, I was given the assignment to test foreign exchange, and what they had, they called them test cases, but it was a list of about 200 test ideas that had been derived somehow from a bunch of use cases that existed for this system. And they were rendered as lines on an Excel spreadsheet. And they were all jumbly and out of order, and cells were merged with other cells. And all of the exchange rates had changed in the previous year. The Canadian dollar had increased in value by about 10%. And I was left with this pile of stuff, basically a bunch of not very interesting test ideas. And since my job was to test the product, I decided that, first of all, I would take these ideas as a kind of point of departure, and I would investigate the product. And I took each one of those ideas, and I explored the product around those ideas, and I found all kinds of interesting stuff. Sometimes the interesting stuff I found was sort of fun. For example, in Canada, there are 5 kinds of banknotes. $5 notes, $10 notes, $20 notes, $50 notes, and $100 notes in common circulation. And this was a teller workstation application. So one of the standard things that tellers do is they take cash from people and put it into their bank accounts, put it into people's bank accounts. So there was a form on the screen. And the form had 6 fields associated with it, 1 for each kind of banknote, plus 1 for change, for coins. And the values that were available, or the fields that were available, allowed you to put in values from 0 to 9,999 notes of each type. So I thought, well, let's try this out. Let's do just a regular domestic receive cash and deposit it to a personal deposit account transaction. So I took a 5 and dropped it into the $20 note field. And I pressed the button, and I verified that this was possible. I verified that the product can work. And then, of course, being a tester, I went to each field in turn and said 9999, 9999, 9999, 9999, 9999. And then in the cash field, $9,999.99. And I pressed the button, and the application blew up so quickly that I thought glass was going to, hit me from the monitor. And this huge, immense Java exception all over the screen. And I went to the local test lead. I was a contractor, so I went to the test lead who worked at the bank, and I said, have a look at this. And he said, what? So I repeated this action. All the nines, and I pressed enter, and this terminal blew up as well. And the answer that he gave me was very strange. He said, no user would ever do that. Besides, you're supposed to be testing foreign exchange. So I had to pause for a minute. I had to pause for a moment and gather my thoughts. Yes, because it struck me as such a bizarre answer. I said, yes, you're right. I am supposed to be testing foreign exchange. Of course, doing that means learning about this system. To test is to learn about a system, after all. So I'm just starting to do that. And of course, part of my process, if I'm going to be testing foreign exchange, is to see if there's any noise in the system that's coming from the domestic end of things, right? If there are problems in the domestic end of things, I don't want to confuse that with a problem in foreign exchange. And so he sort of listened a little bit. And I said, a couple other things. I didn't notice anywhere in the use cases or the requirements documentation where it says that when you overflow certain aspects of the product, it's supposed to spit out this great big Java exception. Moreover, the front end of what we're testing, I'm led to believe, is written in Visual Basic, and I'm seeing this stuff from Java, which suggests that there's a problem deep somewhere in the middleware that is being relayed to the screen. This is not a problem in the front end of this thing. We're going down deep into the system here. And then, if I were to discover a problem like this, would you be interested? And his answer was, I'll never forget, his answer was, well, I guess. What I was experiencing was the result of a very heavily verification-oriented strategy, where people were spending most of their time, those other 5 testers were spending most of their time showing that the product can work, but not investigating the product to find problems in it that might threaten value. At some point, there was some amount of money that this system was unable to handle, and nobody knew what that limit was. A rare problem, perhaps, but the idea that no user would ever do that presupposes the idea that no bank teller would ever act maliciously, that nobody would ever make a mistake, that nobody would ever do anything weird just for fun playing around with the system. Yes, it's unlikely that a user would ever do that, but where are the limits? of what this application is handling. And what are the problems that lead to it spitting out something and not processing strenuous or difficult conditions? Testing is about challenging the product. It's about way more than verification. So a little later on, several weeks later, after I had covered all 200 conditions in the Excel spreadsheet, I decided that what I would do is I would create a system that exercised the transactions so that instead of following a procedure given by some test script someplace, that the testers who used this application, let's see if I can zoom this up to full screen, had a simulator by which they could type a description of a scenario, identify a test objective they had, identify some of the things that they expected to happen and not all of them, and then there's some stuff up here. Let's just go home. It's kind of dark up here. There we go. There's a bunch of stuff there where you could create transactions and you could buy currencies at the top and you could sell currencies at the bottom, and then there'd be all these general ledger accounts available to us. And my little simulator here would use a set of business rules way over on this side, using Excel array formulas to calculate and fire off each rule. I had been told by the project manager for this, you can't do this, it's impossible. And I said to her, well, actually, I think I might be able to. How do you know it's impossible? And she says, well, I tried it myself and I couldn't do it. And I said, well, no, you're a project manager. I'm a tester. I'm way more stubborn than you are. I'm more ambitious than you are. I have a few weeks in which I can try this out. I'm going to have to learn a lot of Excel. And in fact, there are bugs in Excel where the Excel's logical operators wouldn't work inside the array formulas. And meanwhile, as I'm doing this and exploring this and trying to make the rules work on my simulator, I'm learning stuff about the rules on this application and how it works on the inside and how the ledgers get credited, and I'm learning stuff about how foreign exchange works with respect to traveler's checks and with respect to Visa payments and how all this stuff gets processed. And then there's a daily variable rate table, which is over here. And there's 6,000 different entries depending on the kinds of currencies that are being displayed and the amount of currency involved in each transaction, and depending on whether you're buying or selling. And I'm finding out all this kind of fascinating stuff that I never knew about, and finding bugs in the product as I'm doing it. I'm finding out, for instance, that the order in which you do transactions matters. And when I went to the business people and I said, did you know about this? The variation in the bank's profit can go between 10% and 10% one way and 10% another way. Did you know that was there in the system? And he paused for a while. And he said, well, that's a training issue. And I said, wow, this is really amazing. We've got this system that's being developed. The budget for developing this system had been something on the order of $15 million. This machine can make these kinds of calculations. Which is going to be more beneficial to the bank, to the customer, or should we try to be fair? The machinery can make that kind of calculation with both transistors tied behind its back. No problem. But instead of doing that, we're putting the decision in the hands of a bank teller who makes $20,000 a year. We've got this incredibly sophisticated system, but we're going to let this go basically to chance. So I thought it was really fascinating to see the inside, not just of how this system worked, but how decision-making processes were done. This really felt to me like testing. This felt like something interesting and exciting, where I was learning new stuff all the time and telling people stuff that I thought they ought to know about. Way more than walking through a script, and way more than programming a computer to walk through that same script. This was a process of learning and investigation and exploration and discovery, and it was fun. And I got tons and tons of great stories just out of that. It was a reasonably short contract. Lots of really interesting things. Here's another example from the world of medical device testing. My colleague James Bach and I both did some work for this company, and this is a kind of log or a description of some analysis that James did on the medical device. Let me describe what the medical device is like. There's a controller box that an operator sits in front of, and it's connected to a zapper box. And the zapper box delivers to a human patient healing energy. Healing energy. And it's very important for the device to deliver just the right amount of healing energy, because if it's too little, it's not healing energy, it's just energy. And if it's too much healing energy, it turns into killing energy pretty quickly. And if it's the right amount of healing energy for too long, it also turns into killing energy. And if it's the right amount of healing energy for not long enough, it's just energy. So that is the system that we're working with, and one of the things that needed to be tested on this system was how long it takes to cool down after you turn off from the control box the delivery of the healing energy. So I'm going to give you a little bit of vocabulary for some of the things I'm going to talk about here and relate them to this process of verification. First of all, the idea of an oracle. An oracle is a means by which we recognize a problem when we're testing. So it's a heuristic for recognizing a bug when you encounter it. That's another way of putting the same thing. And we've been looking at oracles and looking at ways that we have of recognizing bugs, and we've got three classes of oracles to discuss here. One is a trigger heuristic. A trigger heuristic is something that wakes you up, makes you alert to something, helps you notice something. A radiator heuristic is something that radiates information at you, radiates data at you, or a visualization or description of the data. A decider heuristic is a means of deciding what to do in order to solve a problem. So those are the three kinds of heuristics we're working with here. Trigger heuristics, and trigger oracles, and radiator oracles, and decider oracles. A decider oracle would be something like a specification that has a well-understood statement in it that says the product should do thus and so, and if the product doesn't do that, then we presume that there is a bug there. We have good reason to suspect that there's a bug. Okay. The trouble with verifications is that they can be reasonably good triggers, but they're lousy deciders, and they're lousy radiators. A failing check, and we'll get to what a careful definition of check in a minute, a failing check definitely tells you that you got work to do, you got to investigate. That's a trigger. But a failing check can't decide whether there's a problem in the product, because our first question that we ask is, well, wait, what failed? Did the product actually fail? Could it be broken? Or maybe the check is broken. Or maybe the check isn't relevant anymore. So, it's humans who decide. Checks don't decide whether there's a problem or not. They alert us to the possibility that there's a problem in the product. They're triggers. Log files and screens and data sets and data displays are radiators. And in order to test those things, we have to look at them and evaluate them and interpret them and analyze them and think about them in loops that involve learning. That was a big part of my experience in dealing with the foreign exchange thing. I had to put transactions through and consider what effects those transactions had. I used log files in order to identify what was going on in the system and trace transactions through the system. On the other hand, checks, combined with radiators, can be a really powerful combination. For instance, a check that parses a log file. And if the check is programmed to see something anomalous or strange in the log file, then that can be a powerful combination. But ultimately, it's humans who decide whether there's a problem there or not. So, having set that up, now we're going to talk about this medical device. What you're seeing here, my goodness, there's a lot of data, isn't there? This data represents the stopping point, and then a measurement of the voltage. We'll call it it's wattage, actually. The wattage after 131 specific trials of this system. They were all done in a single day, some in the morning, some in the afternoon. Each line of the display here starts when the button is pressed at the control box, and the operator stops the session, and the measurement continues until we've got 10 measurements, that is to say 1 second, because it's every 10th of a second, of sufficiently low power. According to what the testers had been told was sufficiently low power, 10 milliwatts in this case. And the acceptable time, the testers were told, was 1/5 of a second. That is to say, 2 columns on the chart. Now that's a lot of data to parse, isn't it? So let's take that data, all 131 sessions, and shrink it down and turn it into a radiator, a different kind of radiator. So small that we can't even see it. So tiny that we can't actually see the data. We just see 131 lines of text. And what we notice immediately when we zoom this down is each line here goes beyond 1.2 seconds. So that means there are two, they all fail, if that's the case. If fail matters, all of these are fails. And we can see that at the blink of an eye. That's why we call it a blink oracle. We can make that instant evaluation because each column here, ooh, look at that, it actually works. Each column here ends after that column, after the 1.2 second mark. Now, let's refine the data a little bit, or let's refine the observation a little bit and color when things are too hot. This is over 1 milliwatt, or 10 milliwatts, versus less than or equal to 10 milliwatts. And that's interesting. Now we're seeing a lot of variation in the power, and we also notice right here that the power appears to bounce up again there and there after being turned off. That's interesting. That's going to require some investigation. Then, when we refine our observations still further and put more color on and let human perception allow us to do some analysis of this, we see some weird stuff. Like in the afternoon, it seems that there are more trials that are having trouble with shutting down, and this one in particular. What's the anomaly that we're seeing there? So it seems that on average, the afternoon sessions seem to be longer and a little bit more intermittent, a little more variable. Then we apply something called the low bridge heuristic. The low bridge heuristic says, let's refine ourselves, our observation, as we're getting closer to a target. Like when we're going under a low bridge, we don't necessarily keep going at the same speed. We slow down so that we don't inadvertently bump the bridge. And that makes it easier to see certain ranges of data there. Easier to see now. Let's just turn on Excel's default coloring and see what Excel does with it. And what we see is, oh, wait a second. Without even looking at the individual lines of data, what we see that there are two different ranges of power that we hadn't noticed before. And then we looked at the data and we found out, oh, it's coming from a different starting point. Here, it's starting cooler from a session that's delivering less wattage. Here is a session that's hotter wattage. Cooler, hotter. Cooler, hotter. Interesting. So we've noticed that shutdown is a little bit more difficult from the higher power levels. That kind of makes a certain amount of sense, that if you start higher, it cools down more slowly. At this point, the analysis is going to revolve around the question, well, it's failing according to what we've been told, but how badly is it failing? So let's examine how fast a system shuts down once it actually begins to shut down, and let's change the official shutdown power to 100 milliwatts instead of 10 milliwatts. Because, of course, maybe the specifications are designed excessively precisely. Testing, you see, is not just about pass or fail. In fact, pass or fail is one of the lesser interesting questions in testing. A much more interesting question for our clients is, are you okay with this? Because at the beginning of the project, we don't know all the requirements. We know some of them, we think. But part of the process of deciding whether the product fulfills its business needs or whether it has excessive amounts of risk in it is making an evaluation after we've got more information. In other words, we don't simply assemble or construct software. We develop it. We literally take it out of an envelope. So let's have a look at the adjusted data now after it begins to shut down. And this is looking a little better. Maybe we aren't that far off from good enough. If we can say that 100 milliwatts is sufficiently safe, and the default delivery here is 7 watts of power or 15 watts of power, that the high-powered sessions are 15, lower ones are 7. So all this is less. Everything that we're seeing here is way less than a full power session. Maybe that's good enough for the client, and maybe a third of a second instead of a fifth of a second is fast enough, good enough for the requirements. So what we're doing here is real, honest-to-goodness testing work and not just verifying the truth or falsehood of a statement. For the next thing I'm going to show you, we need a little bit of vocabulary. A client here is somebody who matters, the person that we're doing our testing work for. Aspirations here are what the client wants, what the client hopes for. What would constitute success. Design choices are choices made by the client or somebody working for the client about how good the product is, what it's supposed to be, what we can get from it, and sometimes the aspirations for it are in conflict with one another. The product is an artifact intended to fulfill the specification acceptably. An assertion is a statement or an example that's consistent with something specified. And a specification is a statement that represents a design choice. And then we have a check, an algorithmic process that provides a true or false, yes or no answer based on observing, or operating, observing, evaluating the product based on a decision rule. So this is what verification's all about. Not just the true or false bit, but there's a client who has an aspiration. They make a choice about design. They explicate that choice, and then they express it in terms of a specification, a document or a set of statements. Then somebody comes along to verify the statement. That person has to comprehend the statement, develop a mental model of it, formalize that model for the purpose of designing a check, reify it, that is, turn it into code, turn it into a thing, then design a procedure and turn that procedure into an artifact, a verification procedure based on those assertions. And then the verifier has to set up the environment in order to perform the check, to take it to an artifact, a verification environment, to interact with the product, to collect the data, to take the collected data, which is also an artifact, and to evaluate it. So the verification process involves a human evaluating the outcome of the check and then produces an artifact or a bit that says pass, fail. There's a lot going on here, isn't there? There's a lot of stuff that's happening inside that process. So when somebody comes along and says, oh, don't worry, we can automate all the testing, I call bullshit. Because it's a much richer and much more complicated process than simply getting a machine to produce an assertion. And if we're going to be really good at our craft, we have to think about stuff like this every now and again. So let's go back to C and P, shall we? C reports that P is good if and only if C is good and P is good too. The report generated by C is valid. So if C is good and P is good, then the report generated by C is valid and everybody's happy. Yay. If C is good, it will correctly report that P is bad when P's quality is actually bad, and C's report will be valid. The trouble is that code is often written quickly or under pressure, and sometimes it's written by people who aren't that great at writing code. Whether it's product code or check code, though, code can have errors in it. Now, it's tempting to believe that the product code is more important than the check code because customers don't see the check code. But that leads to a problem, because any conclusion that we might make about P based on the report we're getting from C is risky because the quality of both P and C is uncertain. And we have reason to suspect a lot of the time that C has been developed by people who aren't necessarily full-time developers, or who are new developers, or who maybe are not in this for their development chops. So, that's especially risky. When C is not developed carefully and skillfully, when we as testers are not skillful developers ourselves, there's a risk. If C is not good, C will incorrectly report that P is good, even though P's quality is bad. That means that the report is bad, misleading to us and to our clients. If C isn't good, C may incorrectly report that P is bad, even though P's quality is okay, and the report there is invalid as well. Unless we know C to be good, we can't be sure about the validity of C's report, and that's a real problem, because without investigation and analysis, we can't be sure of the quality of either C or P. After all, wasn't the problem that we had a lot of code of uncertain quality, and now our approach to dealing with it is going to be to write more code of uncertain quality? We must be careful here. And if you think that's bad, we're only getting to the beginning of the problems. C is reporting not just on a single bit, but on a collection of them, hundreds or thousands of individual check results, based on hundreds or thousands of conditions in P. And that means our report is not just all green or all red. There could be lots of stuff going on in it. Now, when there's a failure anywhere, when the report contains a rumor of a failure, a responsible tester won't report that as a bug immediately. Instead, the tester has to investigate and say, is this a real problem in P, or is it a problem with C? But we've already established that neither failing checks nor passing ones are always valid. So what's the problem here? Here are the outcomes that we can get. Number one, a bad product can get categorized as bad because our checks detect problems. Yay, we found real bugs. Or a good product can get categorized as not known to be bad because no problems were found. Yay, yay. Yay, there are no problems that the checks found. But a good product can get categorized as bad because one of our checks is wrong, one or more of them is wrong, which is, yay, we've still got a good product, but we did waste some time and effort. Or a bad product can get categorized as not known to be bad. Not good, but not known to be bad, because none of our checks were good enough to detect that kind of badness. Dang, our checks actually missed real bugs. Now, we're entitled to be happy with the checks. We can say that the checks are good if we believe that 1 and 2 are likely, that is, that our checks are valid, that 3 and 4 are unlikely, which means that our checks are reliable, and C, when our checks don't cost too much. That's how we decide our checks are good. Now, there's something that's come up a couple of times today that kind of bugs me, and that is the idea of flaky checks. Checks intermittently reporting failures. Some people describe those as flaky checks. I don't think they're flaky checks. They're deterministic, after all. They're just code. What might be flaky is your interpretation of flakiness. What are we doing to test the idea that flaky checks are non-problems? It's very easy psychologically to dismiss something as flaky just because it's inconsistent. It seems to me it's important for us to investigate that rather than to try to make flakiness go away. You get to see this a lot of the time. I have some examples of it I could show you during a break tomorrow if you like. If the checks are consistently flaky, why run them at all? Let's get to the bottom of why they appear to be inconsistent. Also, if there's such a thing as flaky checks that are flakily red, what are we doing to make sure that there aren't flaky checks that are persistently running green and misleading us? What are we doing to investigate that? That's a challenge that I try to put before testers, because I've seen this happen at client sites. A lot of the time, the clients will be happily running green checks that are falsely reporting that everything's okay. And isn't there stuff that we could do to use checks to help us test more deeply and more broadly by inducing variation into the checks? Deliberately inducing variation into the checks so that they cover more conditions, cover more factors. On top of that, there are lots of quality criteria that can't be checked easily, like testability and maintainability. What are we doing to find problems that are not found by automated checking? Are we doing too much of that? Are we displacing the time that we have for testing by focusing on this one form of testing, automated checking? Lots of people say, however, that automated checking allows more time for exploratory testing. Is that so? That might be true if the checks are inexpensive and quick and easy to prepare and easy to maintain. We might have more time for exploratory testing if we're not investigating too many failing checks. But if we are investigating lots of failing checks, if we are obsessing or fixating on checks, then we're displacing time that we have for other forms of testing, other approaches to testing. Besides, we might have fewer failing checks if we do more exploratory testing earlier. And in order to understand that, we got to understand what testing really is. Because our contention now is that saying exploratory testing is kind of like saying vegetarian cauliflower. Carbon-based human beings. It's not really very helpful to talk about exploratory testing, because if it ain't exploratory, it's not testing. If we're not learning new things, if we're not covering new ground, it's not testing. So let's call this checking, not testing. Checking is inside of testing. A lot of people have heard about testing versus checking as though they're two different things. They're not. They're not in opposition to each other. It's not like, Manchester United versus Bayern Munich, right? Checking is inside of testing. Checking is operating a product algorithmically to check specific facts about it, like a spelling checker. That means to operate the product using software, to observe it using software algorithmically to collect specific observations, and then applying algorithmic decision rules to those observations, and then reporting the outputs of the evaluations algorithmically. Is there a key word that I might be trying to emphasize here? Is there a key word? Is there a word that seems to weave its way through checking? Checking is the use of algorithms to perform one part of testing, one kind of testing, the part that's on the inside of an evaluation process, a bigger evaluation process. So a check can be performed by a machine that can't think, but has the virtue of being very fast, very precise, or by a human who is sufficiently disengaged, who's been told not to think, and who is slow and variable. But notice, quick and slow here are about the speed of the observable behaviors and the speed of the algorithmic evaluations. The machine will not recognize unanticipated problems. And that's a big deal so far as I'm concerned. It's a mistake to put too much of our trust in machinery and to devalue the human stuff that goes on the outside of the checks, like the design of the check. Checking's fine. There's nothing wrong with checking, but it's mostly focused on confirmation of things that we know or hope to be true. And to escape problems with that, we need to do more than checking. We have to test. So what is testing? Testing includes checking. Checking is a form of testing. It's something that we do within testing. But checking is only a part of this much larger process, which is evaluating a product by learning about it through exploration and experimentation, which includes questioning, studying, modeling the product, observing it, making inferences about it, generating ideas, expanding on ideas, refining ideas that we've expanded on, overproducing ideas, abandoning ideas that we've overproduced, recovering ideas that we've abandoned, recording, reporting, navigating, manipulating the product, developing tools, finding tools, resourcing tools, collaborating with other people. Testing is a much bigger space. I think that we need to be a little bit careful about how much attention we're spending on automated checking. Not that it's bad. It's just not all there is to it. There's lots more that goes on, and maybe I'll have something to say about that tomorrow. Testing is also creating the conditions necessary to do that stuff so that our clients can make informed decisions about risk associated with developing and releasing the product. And in fact, testing is even more than that. It's acquiring the skill, the desire, the inclination, the reputation for creating the conditions necessary to evaluate a product through exploration and experimentation, which, by the way, can include strategically or tactically checking as part of that process. And, by the way, contributing to making a better product by helping the people who need information to get that information. Now, in 2003, James, my colleague, was describing testing, and he, oh geez, look, there's a bug there. It turns out that there was a big bug in the idea of how we were describing exploratory versus scripted processes. We had scripting on the left, but that's a problem because it looks like scripted testing comes first, but it doesn't. In order for checking to be excellent, we have to realize where scripts and checks come from. They come from exploratory work. There's no script that tells you how to read a requirements document. There's no script that tells you how to design a script. There's no script that tells you how to program a check. There is no script that tells you what risks to investigate and what risks you can't investigate with a check. So all this stuff comes from exploratory work. In 2014, we kind of fixed it. We changed it from the exploratory scripted continuum to the informal formal continuum. So informal testing is done not in any specific way, nor to verify specific facts. Formal testing is. And testing doesn't happen in a line, it happens in loops. Loops of testing start with informal, exploratory work, and if we wanted to do excellent automated checking, we've got to embed it in an exploratory process. It's got to start with excellent exploration. So our bug fix is that formality tends to increase over time. So it makes more sense to have formality on the right-hand side of things and informality on the left. So back to P&C. Now we can talk about what doing exploratory testing earlier means. What does it mean? Oh, it includes all this stuff. See? Review and evaluation and learning and sense-making and modeling and studying the specs and risk analysis and recruiting of supporting testers and observation of the product and inference drawing and questioning and task prioritization and coverage analysis and pattern recognition and pair development. And what else does it include? Decision-making, testability, advocacy, design as a test lab, preparation of the test lab, test code development, tool selection, making test notes. I turned this into a rap at one point. You can look at the rap on YouTube because it's really boring for me to list it out like this. Exploratory testing is testing. Verification is more like demonstrating that the product can work. And you need to do all this stuff before and after checking, and you need to do it well for your checking to be good. So how do we come to a better understanding of the status of the product and the quality of our checks? If automated checking is going to be valid and reliable and cost-effective, we've got to put it inside yet another system, which we will call T for testing. And we must challenge our ideas about testing. We must question our testing, study our testing, investigate it. We must question and study our models and our checks and our reports and our ideas about how all that stuff works. Verifications are like a web. Verifications are like a web. And the web looks like this. It's an imperfect web because we have bugs that can fly through the web. Some of the bugs get caught, some of them fly through the web, but we also have litter and leaves and junk that gets caught by the web. The good news is that the testers are the spiders at the center of the web. There's some interesting things. The researchers are finding out about spiders, that spiders sort themselves out based on their temperaments and their personalities. When the researchers look closely at individual spiders, some of them are more likely to keep things tidy, and others are more likely to attack predators, and some of them are more likely to clean things up so that the parasites stay away, and some of them are more interested in repairing problems in the web when there are social spiders involved here. That's just like testing too. We form social networks and social communities within our groups, within our organizations, each of us having different things that we attend to, different things that we specialize in. So the tester is the spider in the web. It's our job to supervise, interpret, and maintain certain kinds of checks and tests. I think it's really important for the developers to do most of the checking work. The vast bulk of the checking work should happen way close to the code. Testers also explore the product, they play with it, they learn about it, they build mental models of it. They specialize in justifying stories about testing, stories about the product. We try to remove our blind spots. We try to improve the value of testing over time. And we adapt our strategies to the project context and to the risk. We explore and investigate and discover risk, and we revise our stuff continuously as we go through that. The big problem that we see with most verification is that it samples very little. It's not very diversified, and the oracles that it uses tend to be kind of weak. Very straightforward kind of assertions about ordinary things. But we could use checking in much more powerful ways, it seems to me, by varying the input and using comparable algorithms in order to verify the outcome of the checks. We could use checks. Somebody came up to me today, I think his name was Dimitri, and I'm not sure if he's here right now, asked me about fuzzing. We can absolutely put fuzzing into a system of checks and use that in order to increase the coverage we get, to cover more factors in the product. Instead of verification, let's consider falsification. We can't verify the idea that the product is okay, but we can falsify that idea like good scientists disproving a theory. And instead of validation, let's consider assessment to develop an informed opinion of the product. And let's be careful about what our checks can and cannot show. We can say that we've not seen any bugs so far, but we can't say that there are no bugs in the product. We can say that we're not aware of any problems yet, but we can't say that there are no problems in the product. So there's my conclusions. I'm flying in with a minute and a half left on the clock. To test is all about investigation. It's about challenging. And doing this requires lots of different kinds of coverage, not just code coverage, not just checking. Automated checks are a fine idea. They reduce some kind of cost, but they do increase other kinds of cost. And we should be aware of those kinds of cost and see what we're getting in terms of value from the checks. Excellent checking is embedded in testing. It's included inside testing, but testing is much more than that. And that's me, and that's done. Oh, you don't need to see that. I want to say thank you to the Heisenbug people for very kindly inviting me to this conference. I'm receiving a very warm welcome, and that's very gratifying. So thank you very much. If there are any questions, I'm happy to take them now. Thank you.
Вопросы-то есть?
Hello, enthusiastic person. Somebody who put their hand up when rapid software testing was mentioned.
Hello, and thank you for this information. I know a lot of it because I read your blog and the James Bach
Thank you.
blog as well. And I want to ask you how do you deal with the not tester's mindset but more of client mindset, because clients, my clients, they usually like these really, really long checklists very much, and sometimes they don't understand that I can do like 2 cases in an hour and next day I can do like 20 cases in an hour because the first time I investigated a lot.
I think, well, that's kind of the subject of tomorrow's talk.
Okay.
But as a craft, we need to get much better at describing our work. The difficulty that we have with our work is that we don't produce tangible outcomes in the same way that developers do. Developers produce code. You can run code, and code does stuff, and you can see that. So it's very tempting for us to act like developers and say, look, we can do code too. But that's not what we're about. We are not... we're more like investigative reporters than we are like people who do stuff. We don't make the laws and we don't make the news. We don't create things that are tangible, that you can touch and see. We need to be able to tell stories. We need to be able to describe things. And the key to it is, my job is to find problems that matter. And there are lots of different strategies for doing that, and that's not just filling out a form. Quick example. If you're going to hire somebody for a job, imagine you're an HR person, you're thinking of hiring somebody for a job. You produce a list of 20 questions for that person to answer. And that person answers each one of those 20 questions correctly. Are you going to hire them just on the basis of answering those 20 questions? Or are you going to interview them? Are you going to ask them a question that they did not anticipate? Are you going to give them a challenge and try to get them to respond to that challenge? Or are you just going to take their answers to 20 questions and say, okay, you're hired? I don't think any sane person would do that for an important job. And I'm presuming that the products we're developing are important products. If it's not an important product, go ahead, just let it answer the 20 questions.
Thank you.
Thank you.
Okay, so thanks. We're maybe out of time now.
We are indeed.
Yeah, but
kind of this red light flashing and all that.
Yeah.
Beep, 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 beep. But you know, I'm not going to let machinery decide. I'm not going to let a machine decide when we're done. If you would like to continue the chat, I'd be delighted to continue it wherever Zenio and Andre want to put me. So thank you. Thank you very much.